Hello everyone, welcome to this session. Earlier we have looked at the stepwise procedure of design of a charge pump PLL and or a charge pump clock multiplier. Now we are going to look at the sources of nonlinearity, in the charge pump PLL, which we are ignoring while designing while finding all the parameters for the PLL. Sources of nonlinearities in charge pump PLL. It appears that these unless these nonlinearities are large, we can easily ignore them. Okay. So, first thing is the following. What we have assumed in the charge pump PLL is a linear gain model for PFD, okay, for PFD plus charge pump both. So, what does it mean? So, let me just draw the block diagram quickly and say, well, we have this PFD, we get we give it to charge pump, right, charge pump, loop filter and followed by VCO. This is what we do. What we have assumed in our analysis earlier was the following. So, this has been the reference, this has been the output, right, and the model of this we have used as phase error detector with plus minus followed by combined gain of PFD plus charge pump is ICP by 2 pi, and that goes to the loop filter and so on. So, here if I have any phase error between the input and the output phase, which is phi error, right, this phi error gets modulated by the charge pump and you get a corresponding ICP gain. This is what we have assumed, which in turn means that let me just plot our PFD response. So, just think about it, that we are having this as a reference pulse, right, and the other one as an output pulse. So, let us say in logged state the phase error is very less or very close, the two rising edges are very close, which in turn means that this rising edges are very close, means the phase error is very small. So, this is the reference and this is the output. So, consider your time instant at this dashed line as t equal to 0. So, at this time instant you get a rising edge on reference, right, and after delta t time you get a rising edge on the output. Okay. What happens as soon as you get the rising edge on the reference, your up pulse go high, okay, and it remains high till the time your out pulse goes high. So, when out pulse goes high, we have seen that it will be having some overlap period and this will go down and this also goes down, fair enough. Okay. So, this is what happens in the actual PFD. Now, if you think about it, that as soon as the rising edge on reference comes, if it comes before the rising edge on out pulse, that means you are going to have a positive phase error. So, this is the phase error, because your up pulse goes high, right. So, you get ICP at the output, a non-zero ICP at the output. Because you get non-zero ICP at the output, you go and change the control voltage of the VCO. You go and change the control voltage of the VCO, which is going to change the rising edge on V pulse, on output pulse. So, a rising edge on reference triggers an up pulse which gives you the current. So, I will draw the current also, that will be helpful for us to understand. It gives a positive current. That current may remain only for this time, but you get this current, and this current itself, you have to highlight it because this is important here. This current itself go and change the control voltage and the rising edge on the V pulse. Okay. So, if at time instant t, let me just write it, if at time instant t equal to 0, phase error between input and output is 2 pi delta t by t. That is what I am looking at without considering, this is what I am talking about without considering that okay, charge pump current comes and it changes the control voltage. If this is the phase error at time instant t, it does not remain the same. Okay. The rising edge, if you think that the rising edge at the output will come at the phase error which you observe at time instant t equal to 0, it is actually not going to be the same, because your charge pump has come into action and it has changed the control voltage, and so it has actually perturbed this edge. You may get this edge before what you may think at time instant t equal to 0. Okay. So, I can write, if at time instant t equal to 0, phase error between input and output is 2 pi by delta t by t, the rising edge on output, will come before delta t time. Okay. Here, by the way, delta t is greater than 0. Okay. Just consider the opposite case. So, what is this opposite case? Opposite case is when you have, I am just showing you in the same waveform. Okay. Let us say when the rising edge on V comes first, and then you have the rising edge on R. They are all frequency locked, so do not worry about that. Okay. So, first I get the rising edge on V. If I get the rising edge on V, then my down pulse will go high first. Okay. And up pulse will go high later when you are going to get a rising edge on out, and this will happen. Now, in this case, rising edge on V has triggered a rising edge on down, which in turn has actually triggered the current also, no doubt. Current is negative. Okay, it has triggered the current. So, current reduces the control voltage, and when it reduces the, this is the current, it reduces the control voltage. When it reduces the control voltage, it is going to shift the rising edge at the output, and the rising edge at the output, this particular current is going to change the next rising edge at the output, because rising edge at the input has already happened. At the rising edge at the PFD inputs has already happened here. So, if I keep the same phase error here it was delta t, here I say the phase error is by the way minus delta t. So, what you see here is for positive delta t, I am changing the output rising edge in the same clock cycle, whereas in case of negative phase error, the rising edge of the output is changed for the next clock cycle. Reference remain fixed, reference is we are not changing the reference at all in this PLL. Okay. So, the response of the PLL is different for positive and negative phase error with same magnitude. If you have positive delta t, it responds differently as compared to the negative phase error. Okay. Well, this is nonlinearity. You will see that during settling, when the PLL is in the locked state and the phase error is very small, this nonlinearity is negligible. Okay. But some depending on the implementation or depending on the phase error which you have, it may happen that you will observe this difference. Okay. And this nonlinearity will then change the loop gain, right. Then the second nonlinearity which we have seen is dead zone in PFD. Well, this is something which we have also addressed by having by having a buffer delay in the feedback path. If you have some finite dead zone where your PLL does not respond, right, then in that particular case it is a nonlinear system. Now, the other nonlinearities which you have observed quite often is, or you will observe, is the static and dynamic mismatch in your charge pump. Mismatch in charge pump. So, what are these? Let me elaborate. Okay. What we have assumed is that we have a switch and this is a charge pump current source. These are ideal current sources, and as we close the switch, a current, a small ICP flows depending on our charge pump current, and these switches are controlled by up and down. Assuming that it is a perfect conversion of the pulse width to the current, whatever we have assumed is correct. But what happens in practice is that you will not have your up and down currents same. Okay. So, if you do not have your up and down currents same, so let us consider the locked state. In the locked state, I am just drawing the up and down overlap pulses. There is no phase error, for example. If that is the case, then if this is up pulse, then our down pulse is also going to be the same. Right. Then during the up pulse, we know that the current which comes out, a small ICP current, is going to be I up, and on the downside it is I down. If I up is equal to I down, then no current flows from this charge pump. But if I up is not equal to I down, or if I say I up is equal to I down plus delta I. If this happens, then what will happen in our actual PLL is that you will have plus delta I current flowing out at every reference clock period. Even when you think it should lock to 0 phase error, it will not. This is what will happen. Now, we have seen earlier that any difference in the current which is pumped into the loop filter every reference period, it is going to create a reference spur. Okay. So, this mismatch between I up and I down current actually leads to the nonlinearity in the PLL, and the PLL does not lock to a 0 phase error, because if you think that you have a 0 phase error, then up and down pulses will be high like this, but in that particular case you will always dump current or charge on the capacitor. So, your control voltage will increase. So, what happens is, in place of in the presence of the mismatch between the up and down current sources, input or your reference and output pulses are shifted in such a way. So, if I up is greater than I down, then you will have a negative phase error such that the overall charge which is dumped onto the capacitor is 0 in one reference clock period. So, what is going to happen is that you are going to lock to a phase offset. Okay. I am assuming that I am having my out pulse, I am having my I up greater than I down, which in turn will lead to the following thing, that I up will come here with the overlap. The overlap period is exaggerated here, that is fine, and down is like this. Okay. So, down is going to be like this. So, we know when I up when down comes first, in that particular case your ICP is going to be minus I down. I am just doing it like this, from 0 level this is going to be minus I down, and when you have up and down both the pulses high, at that time you are going to get this delta. So, this was the mismatch between your up and down current sources, and this is your actually down current. So, the PLL is going to lock to a phase offset, and what is the phase offset, by the way? This is the phase offset. Okay, this is phi offset in phase domain. So, it is going to lock to a phase offset in such a way that the total area under this curve is equal to 0. So, if you have any mismatch between the charge pump current sources, which is actually a source of nonlinearity in your PLL, right, you lock to phase offset, but not to an offset of 0 phase. Okay. Now, we talked about one thing, that you have mismatch between I up and I down. Well, this is actually a static mismatch. What also happens in practice is that the mismatch varies depending on the control voltage. So, if you want to lock your oscillator or lock your PLL to different output frequencies, you will have the control voltage varying over a certain range. So, what you see here is that I up minus I down, or the difference between the top and bottom current, is actually a function of, I would write not proportional, it depends on how you are having, is a function of control voltage. Now, this becomes more problematic in the loop gain, right, because if this is a function of the control voltage, then your offset is going to vary depending on the frequency at which you are locking, your gain will also vary, right. So, this is another nonlinearity. When we are going to design these circuits, we will try to take care of these nonlinearities as much as possible. Okay. Another nonlinearity which is associated with the charge pump is your with your response time of your up and down switches. So, here what we have assumed is these are ideal switches. As soon as we say that okay, the switch is closed, the switch gets closed and current flows, but in practice it is little different. And how it is different? Well, this switch is normally implemented using PMOS and this switch is implemented using an NMOS. So, this is up bar and this is down. So, when I give a signal of up like this, okay, let us say in locked state this is the signal which you want. If this is up signal, then up bar is going to be like this. Okay, this is up bar and down signal is going to be in this manner. Okay. Now, the response time of your PMOS switch is going to be different from the response time of your NMOS, which in turn makes us, let us say, they both are the current values are equal in this case, just as an example, and I am plotting this a small I up and a small I down. So, what happens is this small I up, right, when your up signal goes high here, a small I up current has some response time and it will have a response like this. It is PMOS, so it may have a slower response and it will do like this. This is I up. I down is little faster, so it may do something like this. Right. So, if you look at ICP, which is nothing but I up minus I down, during this time, well, it is 0, but during the transition time, what you are going to see is there is going to be some kind of current like this and then it will have these two areas are going to be same. So, I just do not think, just think that these two areas are same area under these two curves. Okay. So, because of the mismatch in the response time of your NMOS and PMOS, you have the charge pump actually adds current to the loop filter, right, which is again a non-linearity, right. So, one thing is that all these charge pump related issues, whether it is the difference between the I up and I down during like the static difference or because of the dynamic difference, right, based on the control voltage or because of different response time of NMOS and PMOS, they add error to the control volt, they add like ripple on the control voltage. Okay. And they add ripple to the control voltage, thereby adding the reference spur. They also alter the gain of the linear gain of the PFD plus charge pump. If these are within limits, you can still approximate your gain of the charge pump plus loop filter as linear, but in any case they are going to add spurs at the output. Okay. This is one of the non-linearity which is associated. Another non-linearity which is associated with the charge pump is the delay in the loop. Okay. Now, what is this delay in the loop? Well, you look at a frequency divider. Okay. So, the frequency divider which we have in our clock multiplier, which is divided by n clock divider. So, I have your output frequency, here I have a divided frequency, right. So, when I have output frequency and divided frequency, let us just assume that I am using a divide, for example, in this case I am using divide by 2. So, if my output frequency is something like this, right. Ideally, the way I have been using is that I write that my phi div is nothing but phi out by n and so on. Okay. The assumption which I am having is that as soon as I get a rising edge, I start getting the divided clock, and my divided clock is something like this. These edges are aligned, right. If these edges are aligned, you do not get the divided clock at all delayed at all. Okay, you get the divided clock exactly at the same, the rising edge is aligned. But in practice, what happens to the divided clock is that the divided clock is slightly delayed. Okay, this is slightly delayed. So, when the divided clock here is not coming at the same edge, but it is coming at certain delay T d, I cannot write that my phi divided of t, the function here, as phi out t by 2. This is not the case, okay, because what is happening is the divided edge is coming later. So, you can very well say that the divided clock, yes, the phase at the output, whatever phase you are having, that phase is divided, but that phase is actually delayed. It is t minus T d. If you can say in this way also, if you make a change, on the divided clock, on the output clock, then that change is going to be reflected in the divided clock after T d delay. Okay. You make a small change in the output phase, that small change in the output phase is going to be delayed by certain amount. Now, if this happens, then what happens to the transfer function? Then phi div of s is nothing but 1 over n times phi out of s. The transfer function for the delay is going to be e power minus s t d. The delay may be very small, but it is a delay, and this is something which we have not taken into account. Now, with this divided the divider with a certain delay in the PLL, our PLL transfer function is going to be different. So, what will be the new PLL transfer function? Well, you have plus minus for the phase error detector, combined charge pump by phase frequency detector ICP by 2 pi r C1 followed by C2, okay, with a KVCO over S in the feedback, a delay of e power minus s t d, and phase gets divided by n. Okay. This is what we have, which in turn means that you are actually going to have your phi out, the loop gain for the PLL as ICP by 2 pi, okay, KVCO over S square C1 C2 n times 1 plus S pi omega z 1 plus S pi omega P3 times e power minus s t d. Okay. Now, e power minus s t d does not change the loop gain magnitude, okay. It changes the phase. So, the new phase is going to be minus 180 degree plus tan inverse of omega by omega z minus tan inverse of omega by omega P3. Now, what happens to the phase corresponding to e power minus t d? Well, You can directly take into account by substituting j omega, or you can do a little approximation, and that approximation is actually done with the help of e power minus std is approximately equal to e power minus std if std magnitude is much less than 1. If the delay is much lesser than the reference clock frequency, then we can do this. So, if this becomes if this is an approximation of e power minus std, then you see it is like a right half plane 0, and a right half plane 0 will reduce the phase. This is going to be omega times Td. Okay. If you would not have taken this delay into account and then you experience the delay later, your phase margin is going to be degraded, and that phase margin is now then going to be omega u by omega z minus tan inverse of omega u by omega p3 minus tan inverse of omega u by Td. So, this is the degradation in the phase margin which you will see because of the additional delay in the PLL. Okay. If for some reason you introduce any other delay in the PLL loop, you just be aware of the consequence that it is going, any delay is going to add a right half plane 0, and it will reduce the phase margin. Okay. So, this concludes a few of the non-linearities, main non-linearities which we experience in charge pumps. Okay. Thank you.